Welcome to our final installment in aromatic or not aromatic exploration. All of the molecules on the screen here have an atom other than carbon in the ring. This makes them in the family heterocycles. Little reminder about heterocycles when we encountered them in the past. The heteroatom, the atom that isn't carbon, is atom number 1 in nomenclature. And here's some examples to help you naming heterocycles. Back to aromaticity. All of these molecules have a ring structure, so they are cyclic. Criteria 1 has been met for all of them. They must have 4n plus 2 pi electrons to be aromatic. Molecule number A, pyridine, fits the bill when n equals 1. Counting the 6 pi electrons, 2, 4, 6. This molecule is called borazole, named after pyrrole, but borazole does not have a lone pair like nitrogen does, so it is stuck with 4 pi electrons. 4n plus 2 can only be solved with a fraction to make 4n plus 2 equal to 4. 4 times 0.5 is 2 plus 2 is 4, and that means borazole is not aromatic. In fact, it is anti-aromatic once we get finished with the other two criteria. Pyrrole will be using a lone pair on the nitrogen to achieve aromaticity with 6 pi electrons. Two, 4, and after rehybridization into a p orbital, they count as p electrons, that is pi electrons, giving us 6. Oxazole will use, as in the previous video, we'll use only the lone pair on the O to achieve a number of 6. 2, 4, 6. Same story as pyrrole. The lone pair on nitrogen is not necessary, and the other lone pair on oxygen also not necessary. If you were thinking that if you used both lone pairs, the one on the nitrogen and the oxygen, you get up to 10, which fits 4n plus 2 with n equals 2, then you are forgetting that the resonance in a circle can only be achieved with an atom resonating once. All the p orbitals must be the same type to achieve resonance. This next molecule presents a challenge. The nitrogen cannot resonate with the ring unless it uses a lone pair. Similarly, the oxygen cannot resonate with the ring unless it also uses a lone pair. You are forced to use these 4 electrons to resonate, which brings your total to 8. 2, 4, 6, and 8. That presents a situation where n equals 1.5, which does not fit the bill. If you want to make the argument, well, just don't use this lone pair here, the lone pair on the oxygen, just don't use it, well then oxygen is not capable of resonating with the ring, and resonance is lost because you have an atom that's sp3, which can't resonate. That should be n equals 0.5. The next example does not need a lone pair on nitrogen. Nitrogen's already resonating, but oxygen needs a lone pair, bringing the total to 2, 4, 6, 8, 10. That works if n equals 2. Our final example, the nitrogen must use its lone pair, or else it will not be able to resonate. So that counts for 2. Remember, we started with nitrogen down here, rather large molecule. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. This presents a problem. I apologize. That does not create a problem. If n equals 5, 4 times 5 is 20, plus 2 is 22. This molecule, so far, is aromatic. Rules 3 and 4 can be thought of at the same time. Every atom sp2 or sp. If necessary, hybridization can get you there. Rehybridization, sorry. And once you get those required geometries, 4 is also taken care of. Every atom's sp2 in the first molecule. Every atom is sp2 in this molecule. After rehybridization of nitrogen, we're sp2 for all the atoms. Oxygen started sp3, rehybridized to sp2. Nitrogen always was sp2. With rehybridization, so that these can resonate, that makes them all sp2. Everything is sp2 in this molecule. After rehybridization of nitrogen, everything's sp2 in this molecule as well. Summarizing the results, molecule A is aromatic, B is anti-aromatic, C is aromatic, D is aromatic, E is anti-aromatic. F, although it seems to meet all the requirements, is not aromatic. We will have to discuss that shortly. And G is aromatic. Moving back to molecule F. You may not be able to see it very clearly, but there's an orange H emanating off of this carbon and a blue H emanating off of this carbon. Once again, orange H off the bottom carbon, blue H off the top carbon. For this thing to be flat, those H's would have to be in the exact same place, which is physically impossible. So sometimes geometry restricts us from being flat. It has nothing to do with the words over here. It's just you can't have atoms in the same place. So that H and this H, for this thing to be flat, are in the same place, and that's just not possible. So that makes molecule F not aromatic. You can't be aromatic if you're not flat. And one more little interesting molecule to explore. Some of you are familiar with this thing I created for a celebration of the birth of Ray. Upon further analysis, the molecule has 80 pi electrons. That's 40 pi bonds. To solve for n plus 2 equals 80, you have to use a fraction, 39.5, which means the molecule is anti-aromatic. The celebration molecule will not be aromatic. I hope you found this video helpful in your continuing study of aromaticity.